the top of the hour, so I think we should start. So welcome everyone for the last day of the high performance seismology training, our cyber training with different aspects of big data and big computations in seismology. And today is day 4. It's all about high performance computing for seismology. And we have an interesting schedule. So the morning is a little bit more detailed here. We start with a little introduction to 3D earthquake simulations using SeisSol. So the morning part is about learning a little bit about how we can model earthquake dynamics and about the open source code SeisSol. In the afternoon, we will be looking into wavefield simulations using SpecFem 3D. We have about 1 hour of introduction to 3D dynamic rupture simulations and SeisSol, and during this introduction is also your time, to download and test everything. And if something doesn't work, you can please post in the Slack channel, which is monitored by a few people from LME Munich and Scripps. At 10, we have a little breakout for participant introductions. It's something we did on the first day, which was very lively. So please stay around for that. Then we have 3 training examples prepared. The first one is my first 3D dynamic rupture simulation. The second one will be a kinematic model. So that means we're not solving a friction law. I explain that in a second, but we're prescribing how slip evolves on a finite fault. We see how we can model that, in this case with accounting for topography. And then we have quite complex model as the third training example, which is a smaller version of an actually published model from our group that is a scenario for the 2018 Palu Sulawesi earthquake, a strike slip earthquake that also caused a localized tsunami. We have some time for Q&A and more coffee. And then from 12 to 1, there's a lunch break. And from 1 to 2, we will go through the basics of using a HPC system, specifically Frontera. And Ian will walk us through, how to log in, how to monitor jobs, how to submit a job. And we will try one of the 3 examples, the Palu Sulawesi earthquake model on Frontera using a different container, the Aptainer container. So in the morning, we use Docker desktop. In the afternoon, we use Frontera. And this 1 hour in the afternoon is the only part today where we're splitting up, where only some of you have access due to our limited resources. But it's still interesting, I think, to watch and to see how this will work. It's one of the big advantages of both codes that we will cover today, SeisSol and SpecFem 3D, is their community codes. They're open source. They've been also really developed for running on supercomputers. So these Docker environments that we're providing, they're convenient to have your version to go. But one of the big advantages is that, we know they're scaling. They're made for running on large computers. So you can use them for your research if you want to utilize high performance computing infrastructure. Today, morning sessions will be run by me and also by 2 grad students, Sebastian Wolf and Nico Schlieber, both from Munich, visiting San Diego at the moment. And we also have a SeisSol Slack support team, which is Iris Christadler, Mathilde Marchandon, Gina Yun, Jeremy Wong, and Jonathan Klechmann. The last 3 are grad students at Scripps. So please feel free to chat on Slack. There's a large team waiting for your messages for anything related to technical aspects or also the physics of these things that we will cover. All right, so we start with an introduction to 3D dynamic rupture simulations with SeisSol. A few of the most important links right up front. We have a website. This is our GitHub repository. We have a live documentation using Read the Docs, so you can generate a PDF from that if you would like to have a documentation form of a book. But it's also browse or web-based, and everyone can commit changes. So if you see, mistakes in our documentation or something that's missing, it's really easy to extend it. We have our own code of conduct that I'm linking here on the slide that is for contributors and users of SeisSol. And here again, a big shout out to people that were helping putting this training together today. The simulation that's running here is one of the so-called dynamic rupture simulation. So this is a scenario of the 2016 Kaikoura, New Zealand earthquake. And as you can see, this is really not a beach ball radiating waves. It's quite a bit more complicated. We have curved and intersecting faults that at the time in 2016 when this earthquake happened was really surprisingly complex for seismologists, one of the most complex earthquakes ever observed. The earthquake nucleated here in the south and then zigzagged through this complicated fault system, jumping from segment to segment, breaking each fault with partially alternating rupture mechanisms. So we have strike slip, thrusting, strike slip, thrusting, depending on the fault geometry here. And in the warm colors, you also see the seismic waves radiating from each point of the fault that is moving. So as soon as you have acceleration or deacceleration of rupture on these faults, you will emit seismic waves. And the near field wave pattern is really quite complicated. As you can see, we also have triggering by waves. So the earthquake is jumping from segment to segment due to the stresses transferred by waves. A few words on the logistics. As I said, in the morning session, we were using Docker Desktop and ParaView. So this is the part where I explain again how you can prepare if you want to work along with us. Install ParaView, it's not necessary, but recommended. Here's the link to download it. Install Docker if you haven't done so before, and the other days, now is the time to do so. There's a really nice, there's some really nice details about how to set up Docker in yesterday's installation guide. I'm linking that here again. And our Slack channel for today, I think most of you found it by now, is WaveSim Day 4. Any questions for that part? Okay. The next part is the SeisSol specific training image. So we use Docker Desktop for turning your laptop into a supercomputer, as I said before. All the instructions that I have on this slide are also in our training repository. But the steps that you have to do are pretty simple. You basically have to get the SeisSol training Docker image. And for that, you need to run the following command in your terminal with Docker Desktop being launched. So you want to make sure that you have this little Docker symbol up in your active applications line. If Docker is not running, that will not work. One important note is if you are joining today on an M1 or M2 Mac, so one of the newer Mac laptops, OS X laptops, you can test our container with ARM support. That has a slightly different name here. So instead of doing Docker pull SeisSol training, you would do Docker pull and download this test ARM support training Docker that Ian has been working on with many of our group lately. Okay, just a notation. No, what I mean with the $sign. It just means I'm talking about the command line. Okay, and then lastly, if you have that, you can, and that's not in the Slack channel. If you have pulled the image, you can run this command. So Docker run -p 53155 53155 SeisSol training. Or if you want to try the ARM support, instead of SeisSol training, you're putting in this line. And then after some time in your terminal, you should see typically 2 or 3 links popping up there. So they typically look like this. There's some token with some cryptic hash that will change every time you're generating, or every time you're running that Docker image. You can click on this link, or you can copy that link in your browser. And what should happen is then that you see in your browser a little window popping up from which we can navigate to the Jupyter notebooks that we will be using today. So for now, you can just try it. And when we get to the examples after I finished with the introduction, we will show you on the screen how exactly it looks like. So Sebastian will start with that. So please, lean back, listen to me, but don't lean back too much. Try this out and see if you can get the notebooks open in your browser. Okay. A couple of more words here that I wanted to have pop up. So here's just a little cheat box about terminal efficiency. You can use, you probably know that, but you can easily browse back in your history and find your last Docker command if you get confused with how to type it. And we discussed this yesterday a little bit, and there's always this question of how to copy files that are being generated in your Docker image to your local laptop. Sebastian will show you how to do that, but there's another way if you want to advance today, since it's the last day of the training. You could also change how you run the Docker image and add these mount options that are listed on the slide here. For this, you really can mount a directory from which you're running the Docker run command directly into the container, and you will not have to copy files around. So if you're feeling adventurous, or if you want to advance a bit, you can try adding this mount argument. If maybe you want to use the containers in the future, and then it's just easier instead of CPing files around using the Docker commands. Okay. Then the first slide is to thank all SeisSol supporters. So as I said, SeisSol is an open source software project. It has received quite some support from German, European, and US funding agencies. Currently, it's supported by a lot of exascale computing infrastructure projects such as CHEESE, and it's also a characteristic science application of NSF preparing for exascale computing. And we have all in all around 65 contributors over the last 10 years or so. And I talk a little bit about the history of SeisSol, but at the moment, this is mostly a C++ code with a lot of Python wrapping around it, and some Fortran legacy routines are still floating around, I think. There's a couple of links here. So for example, you can learn more about this leadership class application partners. There's a couple of geoscience applications that have been chosen to decide how the next exascale computer should look like. This is a highlight about a long-standing collaboration with the group of Michael Bader at the Technical University of Munich for scientific computing, and then just a couple of logos of the projects that have been helped us funding these efforts. How to contribute. If you get very excited today, please contribute. We have a website that explains how to do it. As a user, the most useful thing is to report issues. And a great way to do that is to use GitHub and create a new issue. You can select an either bug report or feature request. And we have a template of how to do that. We also have some information about how to contribute as a developer. If you click this link, it will tell you how to do that. We have discussion forums, so that's an option that GitHub provides. You have code, you have issues with what I just talked about. Pull requests if you want to participate in development. There's also a discussion forum, and we have some guidance about in which cases it's better to open an issue or a discussion. And you can see some open discussion items here on the screenshot. So all of the interaction with SeisSol is currently organized in our GitHub repository. Okay, so we talk about the computational seismology today. And a quick introduction. Here's a picture of a global wave propagation that you don't see in that form very often because it's using a tetrahedral mesh. So this is already one of the main differences between SeisSol, what we cover in the morning, and SpecFem 3D that you will learn in the afternoon, is the way we're discretizing the domain, either using hexaeders, so rectangles in 3D, or using tetraeders, triangle in 3D. So seismology has been really a pioneering field for high-performance computing. And it's not only, that seismology was pioneered by using big computers, we are also shaping how high-performance computing is done. And this is the case because we have, of course, interesting and very important applications from imaging Earth's interior to, for example, understand the dynamics of the mantle or track down energy resources, to better understanding the fundamentals of earthquake physics. It also has practical reasons. So we as seismologists are typically data-rich. And also our equations that we're solving and our problems can often be treated as linear systems. And that means we can use hyperbolic partial differential equations, such as the wave equation, to describe the problems that we're after. And these really lend themselves to be solved in an efficient way on a distributed computing system. So how HPC has helped seismology is typically by calculating synthetic seismograms. Doing that in 3D Earth is not possible analytically, and also by solving seismic inverse problems for doing tomography, for example. The common approach to do that, and I'm changing the picture to one simulation of seismic waves not traveling in Earth, but traveling through Mars. And this is a simulation that Ebru Bostak has been performing and published in 2017. So the common approach how we're solving these problems is that we seek time domain solutions. So we are looking into how a seismic wave field evolves throughout time of the space-dependent seismic wave field solved by domain decomposition. And so domain decomposition was a little bit touched upon by Ian on day one, but what it means is that we are splitting up our volume in which we're interested in the solution into many small pieces, and we're distributing them across a parallel computing system. There are many ongoing challenges. 3D Earth structure is often not known to the degree that we would like to know it. And it's also, depending on the numerical method and the approximations that we're doing, be complicated to fully integrate in our simulations. Computational efficiency, I'm sure we'll hear more about that in the afternoon, but this is mostly linked to, for example, including higher frequencies or including more multiphysics, and also the complex geological subsurface. And the need for open community solutions. Here's a shout out to SpecFam. There's other community codes that we covered on day one, such as SW4. This is a little bit of a sassy quote by Sharon Drum, who basically said the forward problem for seismic wave propagation is solved. We will see that for earthquake simulations, this is different. The forward problem, our physics are not as well understood as the physics of wave propagation. I also want to highlight that engineers using similar methods, but they're mostly interested in combining different scales and getting more multiphysics into these problems. So here's an application example using the speed code, another open source discontinuous Galerkin code, similar to SeisSol, with a little bit different choices in the specific numerical algorithms that they're using. But this is an engineering seismology simulation of the seismic response of the 2011 Canterbury, New Zealand earthquake, including strong ground motion modeling and soil city interaction, meshing all of these buildings of the city of Canterbury. Okay, so now we're changing to computational earthquake seismology. This is sometimes called physics-based earthquake modeling because we're solving for spontaneous dynamic earthquake rupture at the same time as seismic wave propagation. And there's a lot of nonlinear interaction of frictional failure breaking these faults and the seismic waves that are driving rupture, but that are also interacting with the faults and changing the stresses that are then feeding again in the slip rates of the propagating rupture. So in this framework, earthquakes are treated as frictional shear failure. So shear means we have mode 2 ruptures, when we have no opening typically of the faults. We have only shear 2 shear motion in along strike and along dip directions. So frictional shear failure of brittle solids under compression along pre-existing weak interfaces. So these are our faults. So pre-existing is important because, as you will see, we need to mesh these faults to get them into our simulations. And we're bootstrapping on developments in computational seismology. So what we're doing is really getting these nonlinear descriptions of dynamic rupture of earthquake physics into the same codes that are used for seismic wave propagation using point sources. So it's the same methods, and we are extending them to have this nonlinear interaction with dynamic rupture. This is our typical workflow of the initial conditions and the data that we can use to inform the models and to verify the models. So we have geology is a little bit of a broad word here, but we can use 3D, for example, velocity models, images of fault systems, such as we heard about yesterday from the community fault model, for example, community fault models, topography, bathymetry, information about the subsurface stresses, information about temperature changes to inform, frictional parameters varying with depth, and a whole scale of different input in terms of how the subsurface is structured. We combine this with friction laws that are coming from friction experience, such as the one I showed you here. Then with some ideas about the pre-stress, could be the tectonics, could be simpler models, could be some variability due to fault roughness. We put this together in our volumetric mesh, and we solve for wave propagation and rupture. And we're generating output that can be synthetic seismograms, synthetic ground deformation, or more complicated outputs. So doing this in 3D, and all of the introduction, all of the examples that we're doing today are 3D models, is important if we want to connect these models directly to observations. And it's also useful if you're thinking in a more interdisciplinary context. So for example, the time-dependent ground deformation that we're modeling can serve as an input for tsunami models. So this is what is shown here. It can also be used to understand acoustic wave propagation in the atmosphere. This is one example here for recent work that Sebastian Wolf is involved in, who's one of our instructors today, where we are modeling the seismic banks, the noise of very small earthquakes in Finland. There were magnitude 1.8 induced earthquakes, and they were not disturbing the citizens of Helsinki by strong shaking, but by disturbing earthquake sounds. And this is something we can try and model if we're linking wave propagation with acoustic waves. And this is already a snapshot of the Palu earthquake model that we will look at later that is going super shear. I want to highlight a practical paper that was published by Marlon Ramos, one of our external SeisSol users. So he wrote a really nice review paper about working with dynamic earthquake rupture models in a practical sense. Okay, so earthquake dynamic rupture is treated as a boundary condition in terms of contact and friction. This is what's plotted here in this little sketch. So basically, we're prescribing our fault, and then we have, at least in SeisSol, we have a boundary condition here where we are defining contact and frictional behavior. And very important, earthquake dynamics, what happens on the fault during the simulation is not predetermined, it's not prescribed, but this is really part of the numerical experiments that you will be running. So how our earthquake starts, how it propagates, and how it stops is governed by the initial condition, the loading, the strength of the fault, and an assigned friction law that relates the shear and the normal tractions on this frictional interface with slip rates or slip. Here, two of the most commonly used friction laws. This is linear slip weakening, where we're starting at some static strength of the fault. It weakens with slip accumulating unto some fixed dynamic strength of the fault. So this is kind of similar to understanding of friction based on simple Coulomb friction, maybe, that you have usually higher resistance, at least if you're in the seismogenic part of the fault where you have stick slip, you have higher static friction. Once you start moving, friction drops to some lower dynamic value. And there's velocity weakening, which is part of the rate and state friction formulations, where this drop in friction is not dependent on slip, but on slip rates, on the velocity of how fast our earthquake moves. And the displacement that is accumulating on this fault is what we call slip. So these kind of framework can be numerically implemented really in a range of numerical methods. So in finite difference and finite element type methods, or their higher order derivatives, such as spectral elements or discontinuous Galerkin. They're both finite element kind of methods. And the way this is implemented typically is, for example, by splitting the fault interface. And that's how it's done in most other methods. That means we don't treat this interface just as one defined entity, but we're splitting it. And then these split nodes have to communicate with each other in terms of exchanging information that are related to the rupture dynamics. In SeisSol, we do this a little bit different. The friction law is implemented via numerical fluxes, which has some advantages in terms of not needing to damp any high frequency oscillations, at least with the specific numerical flux that we are using. I have these constitutive laws here. This is just to highlight that we're still solving the wave equation everywhere. So all the codes that you will see today, we're solving the wave equation. We're just adding some physics on the faults which are related to friction and failure. Okay, so much of the complexity that we will see in these models lives in the definition of friction. So how exactly shear traction on our faults is bounded by fault strength, but also in terms of fault morphology. So here's an example of a map view of a dynamic rupture simulation of the 1992 Landers earthquake, in which we also allowed for off-fault damage. So these orange areas here are accumulated plastic deformation, and you can nicely compare this with fault zone width compiled from optical pixel correlation. So high resolution pictures taken by satellites compared before and after the earthquake and reprocessed just recently. And what you can see is that there's a lot of damage in areas of complex fault geometries, right? So if you have a fault bend, if you have a step over, faults intersecting, you're accumulating damage here. And we will see also in our examples that, you know, fault geometry can really add complexity to these models. Okay, so we can build these models at the scale of real observations. So the simulation that's running here is one of these rupture dynamic scenarios of the 2004 Sumatra megathrust earthquake. If we want to do that, there's a couple of challenges. The first one is that earthquake source processes are not easy to measure in situ. In fact, they're often very ill-constrained, plus highly nonlinear, because we have this nonlinear interaction with waves, and also the friction laws themselves are typically nonlinear. So this makes it tricky to come up with, you know, simple models that are tightly connected to observations. The second challenge is to come up with the suitable initial conditions and to decide which physical processes and scales are dominant and relevant for understanding the dynamics of real earthquakes. And the third challenge is more of a technical one. How can we assimilate all of the available knowledge, for example, all of the community models that we talked about yesterday, in a suitable way for software, for modern software, so in terms of the numerical discretizations, the solvers and the equations we are tackling to solve, and hardware, heterogeneous HPC systems, for example, or in terms of energy concerns, and for our community, for example, to make these kind of tools accessible for a wide range of users, to make our science reproducible, and for lowering barriers to using high-performance computing. There's a white paper that I'm linking here, which is talking a little bit in general about, you know, how earthquake modeling is really linked to all of these different scales and different areas of science, from continuum mechanics to applied math to data mining and machine learning. What I want to highlight here is that we're really thinking all the way down to rock experiments, because this is where our friction laws are coming from, and all the way up to space geodesy, because we get data to verify our models from there. So this is a way, these kind of models are a way to connect different fields and different scales. Here, I want to show you one example how this can look like in practice. This is a recent model of the 2019 Ridgecrest foreshock and main shock. And it's a nice example to show, because we're using a lot of the tools that that have been presented yesterday to set up these dynamic rupture simulations. So first, you see two simulations playing. The main shock model, which is playing on this side, sees all of the stresses that the foreshock has caused, and they're running in the same dynamic rupture simulation. But there's no aseismic slip here, so it's just two linked dynamic rupture scenarios. And we are including regional structure, ambient long and short-term stresses, as well as the fault system interaction with a realistic geometry here. And we find that this is quite crucial to understand the dynamics and also the delays of the sequence. So to set up these models, first, we need to, as I showed you the workflow, we need to have an idea about the geometry and about how our model should look like. So in this case, we're interested in getting understanding better how this complex 3D fault network behaved during both earthquakes and how these two earthquakes were talking to each other. So we are using information, the same kind of information that's used for the community fault models, to set up this non-vertical cross-cutting 3D fault geometry. It has to be intersected with topography in the region, and to build up these model that you're seeing here, we're integrating already quite a range of information, from geological field mapping to INSAR data to relocated seismicity and focal mechanisms that informs us of how these faults are extending at depth. Then we're embedding all of these faults in a 3D community velocity model and expose them to the ambient tectonic stress state that is coming from a 3D stress model. And we also, in this case, we're interested in accounting for Coulomb stress changes. So the stress shadows that are left behind by major earthquakes in the same region that occurred over the last 1,400 years. So these can be mapped out and can be also used to inform, the initial state of stress just before these large earthquakes happened. Now, fault strength. Okay, we have our initial loading. That's meaningful, of course, only together with knowing how strong these faults are. And this is a tricky question because similar to the absolute level of stress in the crust, it's difficult to constrain the absolute strength of faults. In this model, we're proposing that these faults are weak during earthquake rupture due to a specific friction law that we're using that accounts for very rapid weakening once earthquakes are as fast as earthquakes are, so faster than around 1 meter per second, and due to also mildly elevated for fluid pressure, lowering the effect of normal stress. We have a way to constrain fault strength based on regional tectonics. So we're looking at the angle of the maximum compressive stress, focal mechanisms in an area to get an idea. And that leaves us with only a few parameters that we need to constrain to understand how this fault system is loaded in its tectonic context. And this is typically initial stress. So in this case, the direction of SH max everywhere in this 3D model, and Coulomb stress changes. The stress shape ratio. So this is telling you how in the tectonic context the amplitudes of the maximum compressive stresses are related to each other. So if you have more of a strike slip regime, a thrust faulting regime, or a normal faulting regime, then a relative fault strength that's relating stress drop and strength drop and fluid pressure. This is just for your information, because we will use some of this in the last and the most complicated example. If you're wondering how the initial conditions of that model are formed, it's following the same ideas. And the relative fault strength, you already see this here, called R, is an important parameter here because it allows us to think about strength and loading of these faults in a relative sense by relating the stress drop to the frictional strength drop. Okay, so this is how this looks like. This is this R ratio. If it's more red, this means it is the fault is a little bit weaker, and if it's more white, it means the fault is a little bit stronger in that area. And here we can also, using these models, we can also understand how these two earthquakes were talking to each other. So for example, we can map out the dynamic shear stresses during the foreshock that's breaking that two faults on the main fault that was hosting the main shock later. And we can also map the Coulomb stress changes here, illustrating how the fault intersection was shadowed by the foreshock, and then later on causing the main shock to tunnel underneath that area. Okay, so the computational cost for these events was around 10,000 CPU hours. As I show you in a second, that number can go up rapidly if you're including more complexity such as fault roughness, and they're interested in higher frequencies. That is work that Nico Schlieva is interested in, who's also one of our instructors. Okay, we can verify these models with a range of observations, and the last example that we are running today has also been verified, against real world observations, for example, of seismic moment release. Can be compared to kinematic models, to back projection, to static GPS and INSAR surface displacement, or continuous GPS and strong ground motion, or Taylor seismic waveforms. And we reach a good fit, which is great because it's not an inverse problem. We're not solving an inversion. This is a purely physics-driven forward model that is then being compared to observations. So this is the observational verification for the foreshock and for the main shock. We don't have to look in this in detail. The main story is that it fits to first order. We can also look into, again, the off-fault deformation. and compared to, for example, damage proxy maps or surface rupture mapping, and looking into qualitative understanding of why certain fault zone width is varying along the fault, and why we have certain areas which have more damage than others. What is the cost of all this? Now, here's an example from Nico's work, where he added not only fault roughness, but maybe also a fault zone, which is a little bit weaker around this complicated fault system, to look into, for example, the effects of a flower-shaped fault zone in specular acceleration. And if you do this higher resolution models, for example, if you're interested in broadband ground motion modeling, going to higher frequencies, we're adding fault zone complexity. Here's just one example, which I kind of scaled up to get a very expensive simulation. So imagine we want to model not only all of this complexity that happens at the source in these two earthquakes interacting with each other, but we also want to reach 15 Hertz in the wave propagation part. And that could require more than 5 hours on 7,000 nodes of Frontera. So this is almost a full machine, not quite, but 7/8 of the full machine, of Frontera, blocking that for 5 hours. If you go to 20 Hertz, that is even a larger mesh of 1.2 billion elements. If you're computing, for example, 5 Hertz, which is a little bit more feasible, we would already need 8 hours on 400 nodes of another supercomputer. Here's an example. So this equates to 170,000 CPU hours. If we would translate that into monetary costs, for example, in terms of energy, imagine that we have 10 cents being charged per kilowatt hour. Probably my number here is a little bit off. That's $220 for the simulation. If we would use AWS without any discount, that would be $6,500. In terms of energy, that is an equivalent to 2 barrels of oils. In terms of carbon, this equates roughly to flying from London to Los Angeles. So this is for one simulation. So that is a very strong motivation to optimize the efficiency of these kind of softwares. We're thinking about the carbon footprint, energy concerns, and of course also accessibility. These numbers are for a specific architecture. There are some supercomputers which are aiming to use less energy. So for example, Shaheen 2 in Saudi Arabia at KAUST. If I would use this one, I could fly a little bit less far from Chicago to Munich. Okay, we are on the path to exascale computing, exascale supercomputing. So what does this mean? Exascale means 10 to the 19 floating point operations per second. So this is a large number, and would be great if we could utilize that for our seismological research. There's a lot of open questions, a lot of research in scientific computing actually to be done to get there. So we need to properly address, vectorization on these machines. Also resilience, what happens if a node fails, which is much more likely on these large machines than on the smaller ones. Energy limits, specialized cores, specialized architecture. It's different to the one we're using now, and how to optimize accuracy per the degree of freedom that we're interested in. So this is me doing field work at TAC, and this is John von Neumann and Robert Oppenheimer in Princeton in 1952, I think. And this is kind of the typical performance developments that you see, how the top 500. So the top 500 fastest supercomputers have been developing over the last 30 years or so, and we can see this steady increase in performance development that we hope that will stay, and that we can reach that for exascale supercomputing too. So there's somewhat of a competition going on between specifically US and Chinese machines, but Europe is also playing a role in clearing the path to exascale supercomputers, setting these machines up, and we as a community should make sure that we are ready for that, and that we are, are still able to use high performance computing on these new machines for our purposes and to advance our science. It's not only that we have exascale supercomputers being installed and running already in some parts of the world. We also have new dense earthquake observatories being proposed or being already installed. So a couple of the examples here that I'm showing, there's a large community effort towards installing RUFSO, so a Rupture fault zone observatory, so very near fault dense observatory. There's SC40, which is subduction zones in 4 dimensions, a huge instrumentational effort to better understand and monitor several subduction zones in Chile and in the US. There's DONET and SNET Japanese efforts, which are already operational, which, for example, include almost 6,000 kilometers of seafloor cable, really improving what we can see in terms of near trench subduction zone seismicity. And we're also entering a golden age of geodetic imaging data with the NISA mission, being coming up at this moment. So these data sets could be utilized together with high performance computing to advance earthquake seismology. If we want to do that, we need to use high performance computing because this enables data-driven and physics-based modeling. So here's an example of using strong ground motion recordings of an Italian earthquake, a normal faulting event in 2016, and we did solve an inverse problem here, but not a kinematic slip inversion, but inverting for the stress and the strength and the friction parameters on the fault. So this kind of dynamic source inversion is reached quite some interesting results, a very nice fit with waveforms, and we learned a lot about the variability of these friction parameters along the fault, but also required 1 million forward models, on the order of 1 million dynamic rupture simulations to get to a best fitting model. Now, if we want to extend that, we can include more physics that we know is important. For example, we add fault roughness, topography, viscoelastic attenuation, and we can then, get towards more realistic also modeling of the broadband seismic wave field content. So that is a paper that has been published that I'm highlighting here, as where we're using these kind of low frequency fit of dynamic source inversion, and we're extending this with more physics, for example, fault roughness and topography. This is just a nice animation. Now you can see the wave field that's emitted by this rough fault interacting with topography, and we're basically finding that high frequency ground motions are amplified early on by adding fault roughness, and then we're adding topography as well to prolong the duration of our waveforms and get to very realistic broadband waveforms in velocity here. So this would be the reference model, then adding fault roughness, adding topography. Now we can see these different effects of increasing high frequency content and elongating the waveforms. We're also able to do these kind of models on megaparsec scales. I already showed you one example. Just go a little bit quicker to that. If we want to do that, we really need to push our numerical methods, not only to utilizing high performance computing infrastructure, but also to handle geometric complexity and highly varying resolution requirements. And there's a couple of information about what we've been working on, what's already under the hood in SeisSol. We have things like auto-generated kernels, so we're not relying on off-the-shelf compilers to optimize how our simulations are done. We have a hybrid or MPI OpenMP parallelization. We use a specific library to read large data sets and write large data sets in a distributed manner. So it's a geoinformation server that was in-house developed. And we're also using clustered local time stepping, and I'll talk a little bit later about this. Our hero run, so using full machines, for example, an earlier one was modeling a subduction zone earthquake that took 14 hours on a full machine. And this same simulation can nowadays, almost some simulation resolving the same physics now requires 5.5 hours on 16 nodes. So this kind of optimization trickles down to everyday research that we're interested in. So we are in seismology, as I think we've seen, data rich during the last days, but we often remain model poor. So here's a machine learning based high resolution earthquake catalog that just reveals how complex our fault structures are that we're interested in. This is the one activated during the central Italy sequence, but it doesn't look very different to other fault systems worldwide. So we have all of this data, but our models are is typically still quite restricted. For example, modeling earthquakes on a simple plane or not accounting for frictional complexities. Here's one example. This is a SeisSol model where we have one fault plane interacting with a fracture network of, I think, 900 fractures in this case, all of them slipping dynamically, and trying to understand how such a distributed fracture network interacts with a main fault. In this case, slip starts in the fracture network and eventually triggers a magnitude 6 earthquake. And this is just a little bit more information. I might skip through this in the interest of time. You can ask me questions about this. Very happy to discuss. That's just one of the applications we can do with a flexible solver as we will be teaching you today. Okay, so SeisSol, as I said, is open source earthquake modeling framework. As I wanted to illustrate in the previous examples, it has a couple of advantages. One of them is that we can represent complex geometries. So we're using unstructured tetrahedral meshes, which is very suitable, for example, for meshing volcanoes, for meshing intersecting fault systems, and accounting for geometric complexity. We have support for heterogeneous media, not only in the elastic sense, but also viscoelastic attenuation, viscoplasticity, anisotropy, and poroelasticity. And in brackets, I have the increase in computational costs, so the overhead of adding this additional physics in the simulation. So if you want to add viscoelastic attenuation, your simulation would be roughly 80% more expensive. Poroelasticity counts in a bit more, and this really depends on the additional equations we are solving. Multiphysics coupling, it's in this, for example, for dynamic rupture, but also for elastic acoustic wave interaction is natural because we have a discontinuous Galerkin method where we can represent discontinuous physics on interfaces. It's high accuracy in space and in time, and high resolution. Well, we can scale up to full supercomputers if we're doing everything right. So DG, discontinuous Galerkin, is quite popular in other wave propagation problems. It's just a shout out to other codes and applications that are using this specific finite element implementation. In short, it's a software allows for rapid setup. I hope we will show you of models with realistic non-planar intersecting fault systems or other complex geometries. It does require extra flops, so it's more expensive than in principle than a finite difference method in terms of storage, in terms of unknowns and time to solution, but we can do that fast and mitigate that by exploiting computational science. Why DG? Couple of motivations. Here, as I said before, basically it has advantages for being able to using unstructured tetrahedral meshes, for example. It also is easy to parallelize. We can use local time stepping, and you can ask me more about this. A couple of more details here. We use a specific numerical flux, specific modal formulation and basis functions. It is just for completeness here. I want to highlight a little bit about the history of how the code developed. We had a geophysics version some years ago, or what I call a geophysics version, which was code written in Fortran 90, MPI parallelized, and using text files for reading and writing output. And this is not how SeisSol looks anymore now. And there was a couple of optimization steps. The first one was when we were trying to win the Gordon Bell Prize. So this is kind of the Oscar for supercomputing. And we performed in 2014 a simulation of the Landers earthquake on a large supercomputer. And to be able to do that, there was a couple of optimization developments implemented. Maybe the most important is this assembler level DG kernels. So that basically means that we are, as I said before, taking over the job of the compiler and have our own generated code that automatically detects and exploits sparse block patterns. So that means we're looking into how each operation looks like within SeisSol in terms of matrix-matrix multiplications. We're looking, if these are sparse-sparse or sparse-dense, if there's lots of meaningful numbers in our matrices, or if it's mostly adding up to 0. And we're doing hardware-specific unrolling and vectorization of these operations, customized for each matrix-matrix multiplication. And in 2014, that was also customized for libxsm, which is a specific library. So we did that because there was no off-the-shelf library that would allow us to optimally compute the kind of operations that we needed in SeisSol for the shape of matrices that we have. In the second step, this is for 2017. This is won a best paper award as supercomputing. We ran this large simulation of a megatrust earthquake, the Sumatra scenario. And if you compare the size of these models, it's not necessarily more decrease of freedom, but it's a lot more time steps. And here, the Lender scenario, we had 200,000 time steps, and we ended up at 3.3 million time steps for this one. And the reason for that is that we implemented something that's called local time stepping. And that means each element can run at its own best time step to keep all of the simulations stable. So if you have areas of the model that have smaller elements that are more complicated, lower wave speeds, they can update more often than neighboring elements that maybe require less computational effort. And all of these optimizations, as I said before, they trickle down to the Docker versions that we will run, and it really helps running smaller models more efficiently. I have a slide about the work that Sebastian did in terms of optimizing anisotropy and polar elasticity. You can ask him about this when he's teaching you about this first dynamic rupture model. But I want to highlight one of the grand challenges that I'm sure many other communities have too, but for us that can really be a bottleneck, and that's the grand challenge of meshing. So how are we generating the meshes that we need to run these simulations? So there's two community standards, as I kind of mentioned before, the hexahedral meshes. So this is what SpecFam uses. They are somewhat limited for complex geometries, but there is good commercial software, for example, Trellis, or I think it's called Qubit again, that can be used to generate these kind of meshes. And there's unstructured TET meshes, which are more flexible. However, there can be also numerically challenging because you can generate something that's called a sliver element. So that's like one really deformed element, one deformed triangle that can break your computational efficiency of the whole mesh. The tools that we will use are GMesh and SimModeler. We're also interested in changing this picture. There's emerging approaches, for example, using curvilinear meshes. So that means the user doesn't have to define all the geometrical complexity anymore in the mesh, but there's a step inside the code which deforms the mesh to, for example, account for topography or even to account for interfaces in the subsurface. SW4 has an implementation for that. We also have papers that are looking into this using different methods. So that is quite interesting. We also are interested in diffuse interfaces, so not meshing interfaces like dynamic rupture or topography explicitly, but thinking about this more in a phase field kind of way and defining diffuse interfaces that are still capturing the full physics. This is advantageous because you don't have to prescribe geometries. You can, for example, have spontaneously developing fractures, as I show in this simulation here. So this is rupture along cracks, that faults that haven't been prescribed. Okay, in SeisSol, what we use today is mostly GMesh or GMSH. This is an open source method that is useful for most simple geometries, everyday mesh sizes, for many of our tutorials, but it is, even if you include topography, what we'll do in the second example, it is limited in terms of support for intersecting geometries still. So for this, we use SimModeler, which is free for academic use, which also comes with a library that we can use. We don't have to use, a graphical user interface to generate meshes that are on the order of hundreds of millions of elements, but can submit that as its own meshing job on a cluster. And the mesh is then provided in a parallel data format, and the code does the internal partitioning. So the meshing workflow, you look at this later a little bit. As I said, either GMSH or SIM modeler. Two snapshots about how their graphical user interfaces look like. Mesh generation problem. I said before, TED meshes can have sliver elements. This is how a sliver element looks like. You have this very tiny triangle that's trying to squeeze in to a fault intersecting with a free surface. This is something that's tricky to spot if you're thinking about, a mesh of, I don't know, hundreds of millions of elements of a subduction zone. So what we're doing in SeisSol is really utilizing this trick of local time stepping. That means if there's a deformed element like this, it will require a very small time step to remain stable in terms of the solution it provides. And we just let it do it to some extent, which is mitigating our meshing problems. So the impact of such a sliver on the whole computation cost, if you don't have local time stepping, if you're using a global time stepping scheme, would mean that one bad sliver can make your whole simulation super expensive or even computational infeasible, because all of the other elements would wait for that one bad or would be doing nothing while this one bad element is updating and calculating. So local time stepping, each element update with its own time step, is what we are doing to mitigate that. There's a little bit of information here. This is basically explaining how much of a speed up you can expect in using this. And we are defining kind of a sweet spot between, clustering some groups of elements, so not really each element is updating with its own time step, but we have clusters of elements that are grouped together that are updating with certain smaller and larger time steps. We're not the only ones that are doing that. It has been implemented in Spectrum 3D, so maybe Brian or Carl can comment on this later if that's part of the main branch. There was a PhD thesis by Max Friedman at ETH Zurich about this. There's also other codes that are interested in that, but it works in other schemes too. Okay, this is a HPS training, so we have to show some speed up plots or some scaling plots. You heard from Ian that this is important. We have these, of course, for SeisSol, which is helpful if you're writing an allocation proposal. And this is just comparing global time stepping versus local time stepping and gives you some speed up on the order of 10. And depending a little bit on the mesh you have, how bad your mesh is. Last comment, visualization. We're using ParaView. Yeah, all the plots that you've seen in this presentation, all the videos, they were generated with ParaView. We have, in terms of output, time series. This is actually still ASCII files, text files of seismograms. We have 2D fields. So this is everything that happens on these faults and on the free surface. So often we're only interested in looking at the waves propagating, and at the free surface where we have data and we don't need the volumetric output. And we have the 3D output field. And we're also using ParaView filters for some simple post-processing, for example, averaging, or slicing or finding cross-sections of data or something. So it's very useful. And here's a shout out to how some of these visualizations can look like. This is animation that Nico generated of the Ridgecrest earthquake sequence on rough faults. We have what happens on these faults, and then you see the waves, the first of the foreshock and then of the main shock breaking here. And this is a visualization that was generated by the VisLab attack, including the volume output of the same simulation. They're usually visualizing astrophysics. I think Ian can confirm that. So this looks more like, some neutron star or something like this, something from Star Wars. Okay. Lastly, what is the future? What can we do? Some kind of vision. What can we do, with exascale computing? Couple of ideas. There's a big push for digital twins and Earth system science. Solid Earth should be part of that. We shouldn't, leave digital twin ideas to climate modeling. And to be able to do that, there's a couple of the things that you already heard about in the sessions before. For example, CyberShake, so physics-based probabilistic seismic hazard assessment, dynamic source inversion. We can think about using HPC to train machine learning-based approaches. And this is work by John Wikowski, which is under review currently, where he's using the output of SeisSol simulations to train reduced order models of shake maps. So we can use these large data that's produced, for example, as training data sets or for adjoint sensitivity analysis, UQ, and trying to figure out how to optimally steer these large instrumentational efforts. We can integrate these methods into rapid response. So one example is the PALO benchmark that we will run later. A lot of the information that we needed to set up this model were available around almost 5 days after the earthquake already. So we can help in the days after large earthquakes to understand what drove these geohazards and what does this mean for the specific region. We can solve more in different equations, pitching timescales and multiphysics. This is a plot using similar methods than what you will learn today, but for seismic cycling simulations. We will not have a tutorial about that yet, but there's a sibling code called Tandem, which is also using DG for complex geometry seismic cycling simulations. And lastly, embracing interdisciplinarity as we're doing here, working with cloud optimization and HPC and services and workflows. And there's actually a lot of projects at the moment worldwide that are trying to push us as a community into this direction. And this is what I have. I think there's some messages on Slack, which is great. But we do a 15-minute break now, and we can have some questions maybe read loud out. And then we start with our first training example. So thanks for listening to me, and I hope you're all set up in the meantime. And let's see how many we are. Then we can decide about the breakouts. Okay, we have 40 people. Should we read out some questions?
Yeah, maybe I can jump in. I already answered some questions about our time stepping. And then there is one question from Ray about teleseismic records. So
let's see. Okay, Ray is asking, I'm curious about whether current dynamic rupture modeling could provide teleseismic records, or we simulate a smaller scale to obtain the source time function during the rupture and conduct a waveform simulation then. Yeah, so that's a very good question. What we're typically doing is we do compare to teleseismic records, but we're not running the simulation on global scale. We can translate our dynamic rupture model into, for example, a couple of point sources. It's even simpler than looking at this at the slip rate functions. And then we use, for example, InstaSeis, which is a really nice platform. Read in our source model, our kinematic source model, and produce teleseismics that we can compare, teleseismic synthetics that we can compare to observation. So that's our current typical workflow. So basically creating a multi-CMT solution after pre-presenting the dynamic rupture model, then using open tools, InstaSeis, to generate synthetics. But this would also work with slip rates, and SpecFam would be better. InstaSeis has still some limitations in terms of axisymmetry. Other question, beyond the physics approach, what's the main difference between kinematic and dynamic simulations in terms of performance? Okay, that's a good question. Under which circumstances a dynamic simulation would be preferred over a kinematic one? So the training examples today will have both dynamic rupture simulations and kinematic simulations. And the main difference is that in the kinematic model, you're prescribing what happens on the fault. So you have a finite fault, you have a time dependence of how slip propagates, but it's prescribed. It's not mechanically consistent necessarily. It can, it's based on data, but there's many different solutions that can fit the same data. It doesn't necessarily confirm with what we know about rupture dynamics and friction. So it's preferred in the sense of physical consistency. That is the main difference. In terms of performance, if you have a kinematic source model, you're not solving the friction law, right? So you're not solving any of these additional equations. Depending on how you're implementing the kinematic source, you potentially need higher resolution if you have a bunch of point sources. and you don't want to filter your seismograms. You might need higher resolution at the mesh in the source region. But typically a kinematic simulation is cheaper than a dynamic one because you're skipping everything that's related to a friction law. You're skipping all these equations. So yeah, the dynamic simulation is preferred if you want to know about rupture dynamics, I would say. Okay. Is there more questions, Sebastian? Is there more that we missed?
No, it's on only these two questions.
Okay.
So
okay.